Hi, I'm Laura Baracchi from Intex, and I will give you an overview of chess and briefly describe the chess methodology. The topics I'll cover during this presentation are the chess objectives, the chess methodology and its component model, the concept of views in chess, and the chess design flow, together with a description of the envisaged process activities across the design views. Finally, I will give a short introduction of the domain-specific extensions that were developed for chess. The main objective of chess was to define a technology that would significantly reduce the whole life cycle cost for the development of high-integrity embedded applications. We adopted a model-based approach where the system development is driven by models defined for the higher levels of abstraction and then progressively decomposed and refined. A technology that allows to reduce the design complexity. An approach that offers the possibility to address different concerns separately, thus exploiting focused expertise. The definition of a process with higher guarantees of correctness, where design errors are caught earlier in the life cycle. A process that fosters components reuse, and the definition of a development process and technology that was sufficiently generic to be fruitfully applied in different domains. Finally, we tried to provide improved tool capabilities to support the overall process. In more detail, the main objectives of chess are to provide a multi-concern component modeling language and a supporting graphical modeling environment that would be able to address the needs of different industrial domains. To enable the specification of extra-functional properties of software and hardware components. To integrate tools for the verification of extra-functional properties. To preserve verified properties at runtime, and all of this to be based on standards and open source material. In particular, we focused on the following aspects. The need to address the complexity introduced by multi-core systems. The need to deal with safety aspects from the early stages of system design. The support for runtime monitoring and verification. Finally, we wanted to experiment this methodology and supporting toolset in some critical application domains, such as avionics or space, automotive, petroleum, healthcare, railway, and telecom. The approach we followed for the definition of the chess methodology is based on the following concepts. On model-driven engineering, so that models are the central development artifacts and that tool-assisted automated development is possible. Component-based development, in particular specialized to capture the extra-functional properties of components, such as real-time and safety and dependability. And also separation of concerns, which is a principle particularly useful to sharply separate distinct aspects of design so that each development actor can focus exclusively on their area of expertise and use specialized formalisms, tools and verification techniques for different concerns. In particular, we focused on separation of concerns related to the separation between functional and extra-functional properties, the separation between different extra-functional dimensions, such as dependability and predictability, and the separation among different design levels and roles. Also, correctness by construction was addressed, so that extra-functional properties can be specified on the model and asserted by static analysis at design time, then guaranteed in implementation, so that they are preserved, monitored, verified at runtime. In the chess methodology, we also adopted a multi-view design space, so that different concerns are addressed in different views. We adopted an incremental and iterative process, where incremental is achieved by designing the system at higher level with its components and then decomposing them. And it's based on the usage of reusable components which are kept in a repository, and based on the composability of components, where by composability we mean that individual components' properties are preserved on component composition, deployment and target, and execution. It's an iterative process, meaning that the static analysis on the model, verification and then back propagation of results is a cycle that can be iterated over until the model satisfies its requirements. In particular, different types of analysis methods are covered. In real-time scheduling analysis, dependability, fault tree analysis, state-based analysis, and failure logic analysis. Another important aspect of the CHESS methodology is that it allows for automatic code generation, like component infrastructure code to realize the non-functional properties of components and their communication, and for support for runtime monitoring and verification. The CHESS methodology relies on the adoption of a component model that enforces the separation of concerns principle. Separation of concerns is achieved by the use of a component model that separates components, containers, and connectors, and uses them to address distinct concerns, where a component is a pure functional unit with its well-defined interfaces. So a component exposes a set of cohesive functional services, and it describes the functional services that are required from other components or from the system in order to operate correctly. This way, reuse of components is enabled under different non-functional concerns, allowing an increased reuse potential. A container is a wrapper which is responsible for the declared non-functional attributes, such as the realization of tasking, timing behavior, fault containment, or fault tolerance, whereas a connector is responsible for the communications. This way, the source code of components is pure functional sequential code, whereas the non-functional concerns are realized and therefore guaranteed by the component model infrastructure. Now I'll give you a brief summary of the CHESS views used to address different concerns. The requirement view is used for modeling requirements at the system, software, or hardware level. The system view is used for system level and dependability modeling. The platform-independent model view is where the user can model components, can define their functional properties to specify the component's behavior in the functional view, and can define their extra functional properties in the extra functional view, where you can model the component's timing and dependability aspects. The platform specification view is where the user can model hardware architecture and dependability aspects of it. The allocation view is used for modeling the software to hardware deployment. The analysis view is divided into a real-time analysis view and a dependability analysis view, where analysis can be prepared and performed. The platform-specific model view, instead, is different from the ones described before, because it is automatically generated, and it's therefore read-only, so that users cannot mess about with it. I'll now briefly describe the CHESS design flow. So first of all, you construct a platform-independent model to represent your solution to the problem, which is independent from any specific implementation. Then, you will complement the platform-independent model with information on the target platform and on the deployment. This way, you will have a feature-rich specification space where also multi-core hardware can be described. Then, at this point, it is possible to perform safety and dependability analysis at the platform-independent model system and software and platform specification level, and backpropagate the results of analysis onto the platform-independent model. At this point, it is possible to have an automatic model transformation which produces a platform-specific model from the user platform-independent model. This is read-only. It's an implementation product which is guaranteed to be deterministic. At this point, we have an implementation, analysis, and execution space where it is possible to perform real-time analysis on the platform-specific model. The analysis results are back-propagated both to the platform-specific model and to the platform-independent model. So these steps from 1 to 6 can be iterated as many times as needed so that the design is adapted until the analysis results are satisfactory. Once this has been achieved, the implementation is deployed to the hardware with runtime verification support if needed. The runtime monitoring is activated at this point to collect live data from runtime monitoring analysis and to backpropagate the results to the PSM and to the PIM. The CHESS toolset and methodology supports the developer through every step of the development process, from the definition of requirements to the modeling of systems architecture, down to the software design and its deployment to the hardware components. As we will see, the CHESS user is accompanied through the whole design flow across clean, single concern design views. I'll now describe the process activities of the design flow across the CHESS views. First of all, we have the requirements view. In the requirements view, requirements can be modeled, organized, and traced to design elements using different kinds of links that CHESS has imported from the SysML profile, such as the derive requirement, the refine, or the satisfy. Criticality levels can also be defined and associated to requirements. So we can see here that modeling criticality is supported with the definition of criticality levels, which can be made to match specific standards like the automotive ASIL, and the definition of dependability and safety criticality extra functional attributes, and the support for automatic criticality validation. In the system view, the user can model the system with the definition of its composing blocks, including, for instance, socio-technical systems that can be modeled using their dedicated profile. It's also possible in the system view to perform dependability analysis, in particular for failure logic analysis, where properties like failure propagation are considered. Once the needed data types are defined or imported from a library or repository, the user can use the functional view to define the interfaces to support the functionalities of system components, the component types, which are strictly functional reusable units, and the component implementations to realize specific component types and allow the creation of component instances. The user can also define the internal functional behavior of the component implementation and its own operations in the behavioral view, using UML state charts and activity diagrams. Here also synchronous block diagrams are allowed in order to provide support for MATLAB Simulink integration. In the behavioral view, we can also model intercomponent interactions using sequence diagrams for the definition of scenarios, which are used in particular for the end-to-end response time analysis. And while defining the component implementation, the user may also switch to the extra functional view to define attribute values for the extra functional properties of interest of the component implementation, like fault occurrence rate. Once the component implementations have been defined, appropriate component implementation instances can be generated automatically. The software integrator at this point is also able to connect together the different component instances using connectors in order to model the global software architecture. Then the user switches to the CHESS extra functional view in order to define the extra functional attributes that apply at instance level, like the worst case execution time estimation for operations, which can depend on specific instance implementations of the component. Now, in the platform specification view, the modeler can define the hardware entities of the target platform, like processing units, memories, or buses, and specify their attributes, such as the number of cores that compose a processor, so we can distinguish between a single core and a multi-core. It's also possible to decorate the hardware platform entities with safety and dependability attributes. At this point in the allocation view, we can model the allocation of the software component instances to the hardware instances that we've created. In particular, in case of multi-core, assistance is provided by the tool to define the deployment with the allocation of tasks to cores. The analysis view is dedicated to the modeling of the analysis contexts used as input for the dependability and schedulability tools. The analysis takes as input the software instances and hardware entities with their extra functional properties related to dependability and/or real-time concerns. Results of analysis are backpropagated to the model for an iterative refinement of the predictability and dependability attributes until the software design fulfills all the requirements. Here, we use the dependability profile and analysis for failure logic analysis and state-based analysis. And here we also perform scheduling and timing analysis also for multi-core, which needed an extension to the MUST tool, which is an external tool which is integrated with Chess. At this point, the PSM platform-specific model can be automatically generated, generating the containers and connectors. With automatic code generation, which includes also the code needed to support runtime monitoring. The runtime monitoring allows to perform simple analysis of runtime traces, statistical analysis of the monitored values, computation of the worst-case execution time bounds for tasks running on a multi-core platform, and runtime verification of functional or extra-functional properties of the deployed application. The Chess methodology is cross-domain, but we also developed specific extensions for some interesting domains. For the telecare, we introduced a profile which enabled us to model, for instance, alert messages. For the automotive domain, we provided support for compliance with AUTOSAR and support for adherence to the ISO 26262 functional safety standard. For the avionics domain, we introduced in Chess the possibility to model ARINC functions and processes and functional partitions, and also to perform schedulability analysis based on these entities. A brief overview of the automotive domain extensions that we provided for Chess. So we studied the possible mappings of the Chess methodology onto the AUTOSAR process. We found a correspondence in the phases of the two approaches, in particular related to the modeling of the application and to the allocation of software to hardware. So we implemented a transformation from the Chess model onto the AUTOSAR model. In particular, from the Chess platform-independent model, we are able to export the application model and the software to hardware allocation, which is modeled in Chess, onto AUTOSAR system configuration files. On the other hand, information about the tasks generated in the platform-specific model in Chess can be given in input to the AUTOSAR process to configure the ECU. Moreover, we introduced an import functionality in Chess, which is able to import MATLAB Simulink models in order to provide tighter integration of Chess with external tools typically used in the automotive industry. For the avionics domain, we introduced in Chess the possibility to model ARINC processes, and we also introduced the possibility to model functional partitions. So to define the allocation of component instances onto the functional partitions that we defined, to define the allocation of functional partitions to cores, where this step can be assisted by the tool, and also to automatically generate functional partitions schedule. Finally, Chess, the Chess tool, can perform schedulability analysis based on these entities.